Very good morning, students. In the last class we are completing borax and orthoboric acid. Today we are discussing third compound, that is diborine. In this concept we are discussing four subheadings, that is preparations of diborine, physical properties, chemical properties and structure of the diborine. First one, when the element E reacts with the hydrogen, it can form EH3. When the element E reacts with the hydrogen, it can form compound EH3, where E is known as boron, aluminium, gallium, indium, thallium. EH3 is only formed but not EH4 and EH5, because the third group element having valency 3, the common valency, the group oxidation will be 3, hence they can form compound EH3, The group oxidation state or group number will be third A. Next student, if the element is equal to boron, that is BH3, which is known as hydrate of boron or borane hydrate of boron, borane hydrate. We know the students, in hydrates the oxidation number of hydrogen is -1, except hydrates they will tell the oxidation number of hydrogen is always +1, except hydrates. In the case of hydrates, the oxidation number of hydrogen will be -1. Therefore, in borane hydride or hydrate of boron, the oxidation number of hydrogen is how much, student? -1. Next one, the BH3, the hydrate of boron, can exist as dimer, that is B2H6. Why it can exist as dimer means to get stability. Every molecule, every atom try to get stability by the dimerization, by accepting electron, by the sharing of electron, lossing of electrons. For example, the trihalides of boron can exist as stable molecule by accepting pair of electron. The trihalides of aluminium can exist as stable molecule by dimerization process. Similarly, the BH3 can exist as a dimer to get stability, that is B2H6. B2H6 is known as diborane. BH3 is borane and BH3 taken part is diborane because it can exist as the dimer. Okay, students. Preparations of diborine. There are four methods are there. We are discussing one by one and step by step, student. When boron trifluoride react with lithium aluminum hydride, it can form diborane plus lithium fluoride plus aluminum trifluoride. When boron trifluoride react with lithium aluminum hydride, it can form diborane plus lithium fluoride plus aluminum fluoride can be formed as the product. It is a reduction reaction. Because boron trifluoride can be converted into diborane. Loss of electronegative element takes place and addition of electropositive element hydrogen will be takes place. Here hydrogen is added, addition of electropositive element. Fluorine is loss of electronegative element. Hence that is reduction reaction. In the presence of lithium aluminum hydride, this reaction takes place. Hence it is known as a reducing agent. This reaction is reduction reaction and lithium aluminum hydride can act as reducing agent. In examination they will ask student, what is the role of lithium aluminum hydride in the above reaction? It can act as reducing agent because in the presence of this reagent reduction reaction will be takes place. Next one, student. When boron trifluoride react with sodium hydride at a temperature of 450 Kelvin, it can form diborane plus sodium fluoride. This reaction also reduction reaction, because again boron trifluoride can be converted into diborane. Loss of electronegative elements and gain of electropositive element takes place, and in the presence of this reagent this reaction will be takes place. Hence again sodium hydride can act as a reducing agent. Next, third one, student. When sodium borohydride react with iodine, it can form B2H6 plus 2 NaI plus hydrogen molecule. This is an oxidation reaction because student loss of hydrogen takes place. Loss of hydrogen means student here reduction reaction. Addition of oxygen, loss of hydrogen will be oxidation reaction. Oxidation reaction. When sodium borohydrate react with iodine, it can give diborane plus sodium iodide plus hydrogen molecule. It is an oxidation reaction because loss of hydrogen takes place. We know that addition of oxygen is oxidation, loss of hydrogen is also oxidation reaction. Next one, student, fourth method. When boron trichloride react with the hydrogen, it can form diborane plus 6 moles of HCl. Diborane plus 6 moles of HCl. These are the four methods of preparation. Next one, student, physical properties of diborane. In a competitive point of view, which of the following statement is not correct and correct? At that time, the statements they will use, student, more concentrate. Don't neglect physical properties also. First one, diborane is colorless toxic gas with the boiling point 180 Kelvin. Diborane is colorless toxic gas with the boiling point 180 Kelvin. 180 Kelvin. Diborane easily catches fire upon exposure to air. When exposure to air, diborane easily catches fire. Easily catches fire. These two are the physical properties, student. Next one, chemical properties of diborane. Chemical properties of diborane. First one, reaction with air. Reaction with air. It burns in the presence of oxygen, releasing enormous amount of energy or a large amount of energy. It burns in the presence of oxygen, releasing enormous amount of energy, that is huge amount of energy. For example, B2H6 react with oxygen, it can form B2O3 plus 3H2O plus 1976 kilojoules of energy will be liberated. Where B2O3 is known as boron trioxide, which is also known as boric anhydride, which we are discussing in the case of orthoboric acid. The boric anhydride can be used to determine the color of the metal in the metal complex, metal oxides as well as the metal complex. Therefore, diborane can react with oxygen. It can form boric anhydride B2O3 plus water plus 1976 kilojoules of energy. That is enormous amount of energy, huge amount of energy will be liberated. Next one, student. The above reaction is an oxidation reaction because addition of oxygen takes place. It is an exothermic reaction because huge amount of energy will be liberated, exited. Hence, it is an exothermic reaction. Next one, student, with water. When diborane reacts with water, it forms orthoboric acid and hydrogen. That is B2H6 plus 3H2O gives BOH taken thrice and 6 moles of hydrogen. That is hydrolysis of diborane gives orthoboric acid H3BO3 and hydrogen. Here the orthoboric acid can be represented in two forms, student. One is BOH taken thrice, another one is H3BO3, another one will be H3BO3. Next one, student, much more concentrate everyone. Every year, competitive point of view, NEET or JEE or KSET, this concept they will be, student, much more concentrate. With the Lewis bases, diborane gives an adduct. With the Lewis bases, diborane gives an adduct. Adduct means addition product. There is no particular name for that compound. Hence, we are giving the name an adduct. Adduct means addition product. For example, B2O3, boron trioxide or boric anhydride, H3BO3, orthoboric acid. But when diborane can react with the Lewis bases, an addition product is formed, that is an adduct is formed. Why? Because there is no particular name for that compound, hence simply you can call it as addition product or adduct. Here Lewis base, what is meant by Lewis base? According to the concept of Lewis acid base theory in equilibrium chapter, Lewis acid is lone pair acceptor or electron pair acceptor. Lewis base is lone pair donor or electron pair donor. Lone pair nothing but electron pair, student. Both ways, both definition you can use. According to the concept of Lewis acid-base theory, the lone pair acceptor is Lewis acid. The lone pair donor will be Lewis base. Here we are using the Lewis base. Lewis base means lone pair donor. Lone pair donor. For example, the lone pair donors or Lewis bases are carbon monoxide can act as Lewis base. Ammonia can act as Lewis base. Trimethyl ammonia can act as Lewis base. Trimethyl ammonia can act as Lewis base. These three compounds we are using to discuss the reaction of diborane with the Lewis bases. Carbon monoxide, NH3 and trimethyl ammonia. First one, student. When diborane B2H6 react with L stands for Lewis base. L stands for Lewis base. It can form BH3L. This bond indicates coordinate covalent bond. We know that the single line indicates single covalent bond, double line indicates double covalent bond, triple line indicates triple covalent bond. We know that. But an arrowhead is present that is coordinate covalent bond. That is boron of diborane and Lewis base. There is a formation of coordinate covalent bond. The coordinate covalent bond formed between Lewis base L and boron of diborane. Lewis base L and boron of diborane. Clear, student? Next one. Why the coordinate covalent bond is formed? How it is formed? We are discussing, student. Let us consider diborane B2H6. It can exist as a dimer BH3 taken twice. When diborane can react with the Lewis bases, the monomer form can react with the Lewis base. The monomer form, that is BH3, can react with the Lewis base. Hence, the BH3 can be written as the diborane B2H6 can be written as 2BH3, which can contains an empty orbital. The boron of diborane, the boron atom of diborane contains an empty orbital. Hence, it is ready to accept one electron pair or one lone pair from the Lewis base. Here, diborane can act as Lewis acid. Whereas we know that the Lewis base always contains at least one electron pair ready to donate a lone pair. Remember, student, L Lewis base ready to donate lone pair, and boron atom of diborane contains an empty orbital ready to accept an electron pair. Here, diborane can act as Lewis acid because ready to accept electron pair, and the Lewis base can act as Lewis base. L can act as Lewis base because it is ready to donate an electron pair. Therefore, there is a formation of coordinate covalent bond between Lewis base and diborane. We know that coordinate covalent bond means the bond formed between the two atoms. But the shared electron pair for the particular bond given by only one atom, but not both atoms. We know that in covalent bond, A atom give one electron, B atom give one electron, one shared electron pair, single covalent bond. For example, A can give two atoms. There is a two shared electron pair, double bond is formed. But in the case of coordinate covalent bond, the Lewis base can give one electron pair. The other substance does not give any electron, but these two electrons are sharing equally. That is known as coordinate covalent bond. The arrow mark indicates the Lewis base can donate electrons to the boron atom. And hence there exists a coordinate covalent bond formed between diborane and Lewis base. Yes, student, it is the structure of an additional product, how it is formed. Next one, student, three examples we are discussing, that is carbon monoxide, ammonia and trimethyl ammonia. First one, student, when diborane, that is B2H6 can react with carbon monoxide. According to the Lewis concept of chemical bonding, the Lewis structure of carbon monoxide will be like this. That is CO triple bond. In between the carbon and oxygen, triple bond is present. Between the carbon and oxygen, triple bond will be present. And each carbon atom contains one lone pair electrons and oxygen atom gets one lone pair electron. In the structure of carbon monoxide, both carbon and oxygen can bond to the triple bond simultaneously, and carbon atom contains one lone pair, oxygen atom contains one lone pair. We know that in diborane, the boron atom contains an empty orbital. This lone pair on the carbon atom can bond to the empty orbital of diborane. It can form 2BH3CO, 2BH3CO. An additional product can be formed. Here, the lone pair electrons on the carbon atom can donate it to the empty orbital of the boron atom. It can form BH3CO, which is known as additional product. Clear, student? Right. Here, we are having some doubt. An oxygen atom also lone pair is there. Is there any possibility to give? Both ways possibilities is there. Either carbon can donate to the boron atom or oxygen can donate to the boron atom. Our concept is electron pair donation to the boron atom. Either carbon or oxygen can donate to the electron pair or lone pair to the empty orbital of the boron atom. An additional product can be formed. Similarly, student, when diborane B2H6 react with trimethyl ammonia, we know that NH3 means ammonia. NCH3 taken thrice means trimethyl ammonia. In ammonia, nitrogen contains one lone pair electron and empty orbital of boron atom is present. There is a formation of coordinate covalent bond between nitrogen atom and boron atom of diborane. It can form 2BH3, NCH3 taken thrice can be formed. Here also there is a formation of coordinate covalent bond between these two. That is an additional product or adduct. For balancing, student, here you will take 2 moles, here also you will take 2 moles. Why? Because 2 moles of carbon monoxide means you have to balance the equation. Clear, student? With the Lewis basis, diborane gives an additional product or adduct. With carbon monoxide, the trimethyl ammonia, there is a formation of coordinate covalent bond with the Lewis base and empty orbital of the boron atom. Copy this, student. Okay, students. Next one, with the Lewis acids, diborane can form additional product. Carbon monoxide we are completing with trimethyl ammonia. And third one is with ammonia. When diborane reacts with ammonia, what are the products formed? Absolutely, additional product is formed. But here, with ammonia, 3 subcases are there. At low temperature, at 450 Kelvin, at excess of ammonia at high temperature. Very, very important, students. With ammonia, these 3 cases combinedly, comparatively will prepare. Definitely one question you will get in competitive point of view. That is, with ammonia at low temperature. When diborane reacts with ammonia at lowest temperature, LT, what happens? An additional product can be formed, an adduct can be formed, which is known as 2BH3NH3. When diborane can react with 2 moles of ammonia at lowest temperature, it can form 2BH3NH3, and an additional product can be formed. Here, same mechanism. The nitrogen contains one lone pair, the boron contains an empty orbital. There is a formation of coordinate covalent bond between these two. An additional product can be formed. Next one. Diborane reacts with ammonia at 450 Kelvin temperature. It can form diammoniate diborane, that is B2H6. 3 moles of B2H6 plus 6 moles of ammonia at 450 Kelvin temperature. It can give 3 BH2 NH3 taken twice plus BH4 minus, which is an additional product or adduct, which is known as diammoniate diborane. Hence, which is on further heating, and a very interesting compound is formed, that is known as B3N3H6 plus hydrogen. B3N3H6 plus hydrogen. That is known as borazole or borazine or inorganic benzene. B3N3H6 are known as borazole, borazine or inorganic benzene. When diborane reacts with ammonia at 450 Kelvin, an additional product is formed, which further heating forms forms borazole, borazine or inorganic benzene. The structure of the borazine similar to that of benzene, similar to that of hexagon structure. Hence, it is commercially known as inorganic benzene. In examination point of view, they will ask, what is inorganic benzene? Borazine or borazole are known as inorganic benzene, which is having molecular formula B3N3H6. The structure of the benzene, like the students, we know that in benzene ring, the 6 carbon atoms are arranged at the 6 corners of hexagon, and in between the carbon atoms, double bonds are arranged alternatively, and each carbon atom can be bonded to the one hydrogen atom with the molecular formula C6H6. And how many sigma bonds, student? 12 sigma bonds. Between the carbon atom, 6 sigma bonds. Carbon and hydrogen, 6 sigma bonds. Totally 6 plus 6, 12 sigma bonds. And there are 3 pi bonds. That is well-known structure. And borazine or borazole. Here the boron and nitrogen atom arranged alternatively. Boron, nitrogen, and nitrogen. And each boron and nitrogen atom can be bonded to the one hydrogen atom. And in borazine structure, there is a formation of coordinate covalent bond between nitrogen atom and empty orbital of the boron atom. We know that nitrogen contains one lone pair of electron, boron contains empty orbital. Hence, the arrow mark indicates coordinate covalent bond is formed from nitrogen to the boron atom. Let us see, student, nitrogen group 15 element or 58 contains 5 valence electron. Here 1, 2, 3 bonds are present. Therefore, 3 valence electron. Remaining 2 electrons can exist as the lone pair present on the nitrogen atom. That 2 electrons can form coordinate covalent bond with the empty orbital of the boron atom. Just now we are discussing. The boron contains an empty orbital. Therefore, in borazine, around the nitrogen atom, 4 bonds are present. Similarly, around the boron atom, 4 bonds are present. Clear, student? Here, nitrogen atom can form coordinate covalent bond with the boron atom. In borazine or inorganic benzene, the coordinate covalent bond is formed from nitrogen to boron atom. Nitrogen donate lone pair of electron, boron accept lone pair of electron. These two structures are nearly similar to each other. Therefore, in organic chemistry, C6H6 is known as benzene. In the inorganic chemistry, B3N3H6 is known as inorganic benzene. Inorganic chemistry, benzene ring structure will be present. Hence, it is known as inorganic benzene. Hexagon ring is present. Each atom is bonded to one hydrogen atom, and 3 pi bonds are arranged alternatively. One sigma bond, that is coordinate covalent bond. Another bond will be pi bond. 3 pi bonds, 6 hydrogen atom arranged alternatively. Hence, it is clear that B3N3H6 is known as inorganic benzene or borazole or borazine. Here, in examination point of view, student, what is the ratio of the sigma and pi bonds in borazine? They will ask. Sigma bonds are 12 and pi bonds are 3. 12:3 or 4:1. 12:3 or simple ratio will be 4:1. Similar to that of benzene also 12:3. Hence that is 4:1 is the ratio of the sigma and pi bonds. Clear, students? Next one, third condition. With excess of ammonia at highest temperature. When diborane reacts with excess of ammonia at highest temperature, it can form boron nitride. The formula Bn taken x times. The boron nitride resembles the structure of graphite. We know that in our lower classes, graphite is having layer structure which can act as the lubricant. Similar to that of boron nitride is also having the layer structure. Hence, the structure of the graphite resembles that of the boron nitride. The structure of the graphite resembles the structure of the boron nitride. In examination, they will ask the structure of the boron nitride resembles that of which of the following: diamond, graphite, fluorine. They will give graphite and boron nitride are having similar structure, that is known as layer structure. One layer slides over the other. Okay, student, when the product is formed, when diborane react with excess of ammonia at the highest temperature, it can form boron nitride. Bn taken X times. That X may be 3 or 4. 3 means 3 layers are present. 10 means 10 layers are present. Why? Because it is having layer structure. One layer sliding over the other. Okay, student. Next one. Fourth property. With oxygen completed, with water completed, with Lewis bases will be completed. With Lewis bases, 3 conditions with ammonia, student. What is that? At lowest temperature, at 450 Kelvin, excess of ammonia at highest temperature, more concentrated. The fourth property, when B2H6 diborane can react with hydrochloric acid, it can form B2H5Cl plus hydrogen. Similarly, when fifth property, when diborane can react with chlorine, gas, it can form boron trichloride plus hydrogen gas. Similarly, when diborane can react with sodium hydride, it can form sodium borohydride. Similarly, when diborane can react with lithium hydride, it can form lithium aluminum hydride. Here the sodium borohydride as well as lithium aluminum hydride can act as strong reducing agent in organic synthesis. In the second PU students, the sodium borohydride or lithium aluminum hydride, the reducing agents reduces carboxylic acids to aldehydes and aldehydes to the alcohols. At the time we are using the reducing agents, so those are sodium borohydride and lithium aluminum hydride. How they can reduce carboxylic acid to aldehydes and aldehydes to alcohols? So in detail we are discussing in our second year. In first PU, only this information is there. That is, the sodium borohydride and lithium aluminum hydride can act as strong reducing agent in the organic synthesis. In our PU board point of view, they will ask question like, name any 2 strong reducing agents which are useful for the organic synthesis. Sodium borohydride NaBH4, lithium aluminum hydride LiAlH4. Clear, students? Right. Copy this. Okay, next continuation, student. Last concept in diborane. Preparation, physical and chemical process are completed. Fourth one is structure of diborane. Okay, students. In diborane, boron atom can undergo sp3 hybridization. According to concept of sp3 hybridization, one s orbital overlap with 3p orbital to form 4sp3 hybrid orbital. In diborane, the monomer form is BH3. Hence, the surrounding atoms are 3 hydrogen atoms. 3 single electrons are required. For example, boron atomic number is 5. Electronic configuration is 1s2, 2s2, 2p1. In detail, 2px1, 2py1, 2py0, and 2pz0. It is 2py0, students. Okay. The electronic configuration is 1s2, 2s2, 2px1, 2py0, and 2pz0. Here only one single electron is present, but you can require 3 single electrons. Hence, excitation phenomena will be takes place. Therefore, one electron from 2s2 orbital jumps to the 2py orbital. Hence, the electronic configuration is as follows: 1s2, 2s1, 2px1, 2py1, and 2pz0. Therefore, 3 single electrons are sufficient to form a diborane molecule. Hence, one 2s orbital, 2p or 2p orbitals overlap with one another to form 4 sp3 hybrid orbital. H1 is a hybrid orbital. 1 2s orbital, 3 2p orbital. Here empty orbital is also present, student. In hybridization, one important condition is there. Not only single electron containing orbital, but also empty hybrid orbitals. Empty orbitals also can involve in a hybridization. Recall that point, student. In hybridization, not only single electron containing orbitals, but also empty orbitals also involved in hybridization. Because boron atom can undergo sp3 hybridization. 1 s orbital, 3p orbitals are required. Therefore, 1 2s orbital, 3 2p orbital overlap with one another. 4 sp3 hybrid orbitals are formed. Among the sp3 hybrid orbital, 3 hybrid orbitals contains single electron. Because of the 3 electrons only. And another hybrid orbital is also present, that is empty orbital. Please, students, once again I will recall that information. The electronic configuration of boron is 1s2, 2s2, 2px1, 2py0, 2pz0. The electronic configuration of hydrogen is hydrogen 1s1. We know that in B2s6 hydrogen atom is also present. Very clear. Here, one single electron is present, but can require 3 single electron. Because BH3 diborane, 3 single electrons are required. Hence, one electron jumps from 2s orbital to the 2py orbital. The electronic configuration is 1s2, 2s1, 2px1, 2py1, 2pz0. Hence, 3 electrons are available. Therefore, 1 2s orbital, 3 2p orbital overlap with one another to form 4 sp3 hybrid orbital. Among these 4 sp3 hybrid orbital, one orbital is empty, does not contain any electron. Since the hybridization is sp3, therefore the 4 sp3 hybrid orbitals are arranged at the 4 corners of the tetrahedron. Here, this dotted line is the empty orbital. Remaining 3 are contains 1 electron. Boron contains 4 empty. Boron contains 4 hybrid orbital. Among these 4, one is empty orbital. That does not contain electron. Remaining 3 contains 1 electron in each hybrid orbital. Similarly, here diborane 2 boron atoms are present. Another boron atom also same condition. One is empty orbital. Remaining 3 orbitals contains 1 electron each. It can contains 1 electron. Here what happens to it? These 2 hybrid orbitals of the boron atom overlap with 1s orbital of hydrogen atom of diborane. What happens? Normal sigma bond is formed between these 2. Boron can give 1 electron. Hybrid orbital of boron can give 1 electron. And 1s orbital can give 1 electron. There is a formation of sigma bond between these, normal sigma bond. Like this boron, this hybrid orbital of boron atom, this one and this one. These two hybrid orbital can overlap with the 1s orbital of hydrogen atom to form normal sigma bond. Clear, student? 1s orbital hydrogen atom, electronic configuration 1s1 contains 1s electron. Okay, student. These orbitals are completed. Then what about remaining? Here another hybrid orbital of boron atom contains 1 electron. Here another hybrid orbital of another boron atom contains empty orbital. But among the 6 hydrogen atom of diborane, 4 only completed. In our hand, remaining 2 hydrogen atoms are there. Therefore, the hydrogen atom contains 1 electron, can overlap with both these orbitals. Here, twisted point, student. If 2 electrons are present, 2 atoms are required. But here only 2 electrons are present. One is from hybrid orbital of the boron atom. One is from 1s orbital of hydrogen atom. This orbital is empty. Even though it is also involved in overlapping. That is, the hybrid orbital of the first boron atom, 1s orbital of the hydrogen atom, and empty hybrid orbital of the second boron atom. Overlap with one another continuously to form a sigma bond. This bond is known as 3 center 2 electron bond. 3 center 2 electron bond. Why? Because 1, 2, 3 boron atom, hydrogen atom, boron atom. 3 centers are involved. But how many electrons are shared, student? Only 2 electrons are shared. Generally, between the 2 atoms, 2 electrons are shared. If 2 electrons are present, 2 atoms will share. But here 2 electrons are present, 3 electrons are shared. 2 electrons are present. One is hydrogen, one is from first boron atom. But how many atoms are sharing, student? 3 atoms. Boron, hydrogen, boron atom. This type of bonds are known as 3 center 2 electron bonds. Centers are 3, that is atoms are 3, but sharing electrons are only 2. Why? Because this to get stability. In this method, both boron and hydrogen atom gets stability. Similarly, student, the hybrid orbital of the boron atom contains 1 electron. The empty orbital of the first boron atom does not contain an electron. But among the B2H6, among 6 hydrogen atom, 1, 2, 3, 4, 5 hydrogens are completed. Another 6 hydrogen atom is there. That is, 1s orbital of the hydrogen atom can give 1 electron. Second boron atom can give 1 electron. With the third empty orbital of the boron atom, overlapping takes place continuously. You can form boron hydrogen bond. Boron hydrogen boron bond. Boron hydrogen boron bond, which is also known as 3 center 2 electron. 3 center 2 electron bond. Sharing electrons are 2, but the number of atoms are 3. Hence, it is known as 3 center 2 electron bond. These bonds are also known as BHB bond. Boron hydrogen boron bonds. But these bonds are known as just boron hydrogen bond. Boron hydrogen bond. Due to this reason, these two hydrogens are known as terminal hydrogens. Terminal hydrogen. And these two hydrogens are known as bridged hydrogens. Bridged hydrogen, because these two hydrogens form a bridge between the two boron atoms. These two hydrogens and these two hydrogens end of the molecule, terminal of the molecule. Hence, those 4 hydrogens are known as terminal hydrogen. Terminal hydrogen. One important point, student. In diborane molecule, the number of BHB bonds or 3 centered 2 electron bonds are only 2. This is 1. This is one, total 2 bonds. In diborane molecule, BH bonds are, that is 2 centered 2 electron bonds are 4. 1, 2, 3, 4 bonds are present. It is the orbital diagram of the diborane molecule. Orbital diagram of the diborane molecule. Hence, in examination they will ask, what is the hybridization of the boron atom diborane molecule? That is sp3 hybridization. Next, student, in NEET exam this question is given. That is, how many hybrid orbitals involved in the diborane molecule? How many hybrid orbitals involved in the diborane molecule? How many, students? 8 hybrid orbitals, because each boron atom contains 4 hybrid orbitals because of the 2 boron atom. Here 4, 4 plus 4, 8 sp3 hybrid orbitals are present in a diborane molecule. Clear, student? Next one. After orbital diagram structure, the structure of the diborane will be like this. The structure of diborane will be like this. These two and these two are terminal hydrogen. The bond angle between the two bridged hydrogens and boron atom. Two bridged hydrogens and boron atom will be 97 degrees. Whereas the bond angle between two terminal hydrogens and boron atom will be 120 degrees. The bond length between terminal hydrogen and boron atom will be 119 picometer. The bond angle between bridged hydrogen and boron atom will be 134 picometer. Memory based value, student. Here, bridged bond angle less than that of the terminal bond angle. Bridged bond angle less than that of the terminal bond angle. Whereas the bridged bond length more than that of the terminal bond length. Bridged bond length is more than that of the terminal bond length. That two concepts you can remember, student. Competitive point of view, expected question. Next one is, in the diborane structure, the 4 terminal hydrogen atom, the 2 boron atom lies in the horizontal plane. You can observe, student, the 2 boron atom and the 4 terminal hydrogen atom are lies in one plane, that is a horizontal plane. Whereas and the two bridged hydrogens are present in a vertical plane which is perpendicular to the horizontal plane. The two boron atom and four terminal hydrogens are present in a horizontal plane. The remaining two bridged hydrogens perpendicular to the plane of the boron atom. Yes, students. Right. In competitive examination, they will ask, how many maximum number of atoms present in the plane of the diborane? How many students? Totally 6 atoms. 1, 2, 3, 4, 5, 6. Horizontal plane contains maximum number of atoms. Vertical plane contains minimum number of atoms. Two bridged hydrogen atoms are present. Next question. The simple structure of diborane will be like this. Boron atom can be bonded to four terminal hydrogen atom. The two boron atom form bridge by using two hydrogen atoms. These two bonds are known as BHP bonds. Boron hydrogen bonds are three-centered two-electron bonds. These bonds are also known as banana bonds or tau bonds or multi-center bonds. Banana bonds. Why? Because the shape will be like this in the form of the twisted banana. Hence, these bonds are also known as banana bonds or tau bonds or multi-center bonds. More than two centers are present. Multi-center bonds. Clear, student? BHP bonds, three-centered two-electron bonds, banana bonds, tau bonds or multi-centered bonds. Total how much, student? Two bonds are present. These bonds are 2 in number. Whereas BH bonds, two-centered two-electron bonds are 4 in number. 1, 2, 3, 4 are 4 in number. These questions are more expected in examination. Student, structure of diagram will be important. Copy this, student.